to my today's session with some question bank discussion of the electromagnetics. Already we have discussed some questions of electromagnetics in previous class. These are some more questions discussion. Myself Dr. Sayanti Chatterjee, Associate Professor of Department of Electrical and Electronics Engineering in IARE Hyderabad. So today we will start our next topic. So what is the course outcome? So the course outcome already we have discussed. We will discuss about the electromagnetism. So we are moving to the question number 1. Define magnetic induction, magnetic field, magnetic flux density, magnetic field intensity, permeability, and magnetic susceptibility. So this is a definition type question. So we will start from the magnetic induction. What is magnetic induction? Induction of a magnetism in a body when it is in a magnetic field, or if any magnetic flux set up by the magnetomotive force, we can tell it is the magnetic induction. Say we have a magnet near our hand and we are bringing any magnetic material like iron, cobalt or nickel near to it. It will also turns into the magnet, or if we rub the magnetic material with a magnet, it will turn into the magnet. So what is the physics behind it? The magnetic flux has been set up due to the magnetomotive force. What is the meaning of magnetomotive force? The force required to bring a unit pole from infinity to one magnetic field. So this is called the induction of magnetism. Next one is the what is the symbol? We will write with magnet B, and it is also known as the magnetic flux density. So this is also known as the induction of magnetism. We are moving to the next question. What is magnetic field? So magnetic field is nothing but the area where if we keep any magnetic material, it will experience some force. Now, what is the magnetic flux density? Magnetic flux density we wrote by B. Magnetic flux density is equal to total magnetic flux. Magnetic flux we write by phi divided by A. A is the surface area. Magnetic flux is a fictitious quantity. This is not a practical quantity. What is the importance of the magnetic flux? Magnetic flux means if we keep one unit positive pole in a magnetic field, the path it will follow is known as the magnetic lines of force or magnetic flux, and magnetic flux per unit cross-sectional area is known as the magnetic field. What is the magnetic field intensity? Magnetic field intensity is known as the So what is magnetic flux density? Magnetic flux per unit area. We can also write by B is equal to d phi by ds. And what is the unit? Unit is Weber per meter square, and we can also call it by Tesla. By integrating the both side, we can get the total magnetic flux. Phi is equal to ds. Next, we will discuss about the magnetic field intensity. So what is magnetic field intensity? The magnetic field intensity is known as the force required to create the magnetic flux. Next one is the permeability. What is permeability? Permeability is the inherent property of the core which helps to sustain the magnetic flux in the core. How much sustainability is there to hold the flux? That like iron, cobalt, nickel, they have the more magnetic flux. And how we can write the permeability? Permeability is written by mu. Mu is equal to B by H. What is B? B is the flux and flux density. What is H? H is nothing but, what is H? H is nothing but the magnetic field intensity. Now we are moving to the next question. So what is the relation? Relation is B is equal to mu H. And what is mu? Mu is equal to mu naught mu naught. What is mu naught? Mu naught is the absolute permeability or permeability of the air, and the value is taken as 4 pi into 10 to the power minus 7 Henry per meter. The unit of mu 0 is Henry. What is mu1? Mu1 is the relative permeability. What is the meaning of the relative permeability? With respect to air or vacuum, what is the permeability of the medium is known as the mu1, or it is also known mu-r, and it is also known as the relative permeability. Relative permeability generally varies with the core to core. Next question is the last is the magnetic susceptibility. In electromagnetism, the magnetic susceptibility, we generally write it by Xi, is the measure of how much material will be magnetized if we give the magnetic field. It is the, so see, we have a magnetic core. It is made of either iron or silicon steel or CRGO, like this different material of iron. Now, if we want to turn it into the electromagnet or magnet, how much magnetism is required, how much force we will give to convert it into a magnet. So magnetic susceptibility is written by zeta, is a measure of how much material will become magnetized in the applied magnetic field. It is the ratio of the magnetism M, that is the magnetic moment per unit volume, to the applied magnetizing field intensity H. We can write that first is the constant K is equal to I plus H, and if the total flux density is B, actually B is B due to the magnetic field and B due to the intensity of magnetization of the bar. What does it mean? We have a magnetic bar and we have a iron. We have induced the magnetism on the iron bar. So what is the total flux density? Flux density due to the magnetic field as well as due to the intensity of the magnetization bar. So B is equal to mu naught H plus I. What is I? Due to the magnetization of the bar. So again, we know that what is the B? B is equal to mu plus B by H. What is B? B is nothing but the, what is B? B is the total flux density or flux density of the medium. So B is equal to mu naught mu r H plus mu naught H, and I is equal to K into H. So we can write B is equal to mu H plus mu naught H plus K is equal to I into H. Now, what is, sorry, I is equal to K into H. So if we cancel the H totally, so we will get mu is equal to mu naught into K. And what is mu? Mu naught mu r is equal to mu naught plus K. So this is known as, if mu r is greater than 1 for paramagnetic, mu r less than 1 is for the diamagnetic, and mu naught is equal to 0 for the non-magnetic. This is paramagnetic, diamagnetic and non-magnetic material. So what is the magnetic susceptibility? Magnetic susceptibility is K, or sometimes we write it by zeta. So magnetic susceptibility we have discussed. So we are moving to our question number 2. State and explain the importance of Bio Savart's law for electromagnetic fields. So for the Bio Savart's law, so we are discussing about the Bio Savart's law. So what is Bio Savart's law? Bio Savart's law tells about the relation between the current carrying conductor and magnet in an electromagnetic field. So let's assume there is a current carrying conductor and there is an P is a point. We have to calculate the force between these two. So say this is the magnetic field intensity due to the current element IDL is DH. We are assuming when current is flowing through a current carrying conductor, there is some magnetic property and the magnetic field intensity of the current carrying conductor IDL is DH at the point P. This is our DH. And what is the value of the H? H is equal to current into length. So it is, if the current is I, so it is I into DL. We are thinking about an infinitesimal, very small length of the electric conductor. So according to the Bio Savart's law, DH is directly proportional to the IDL. Next, again, DH is also directly proportional to the sine theta. What is theta? Theta is the angle between the current element and length of joining the point. DH is directly proportional to the sine theta. What is sine theta? Angle between the current element and length of joining the point. And also DH is directly proportional to the R. What is R? R is nothing but the distance of the current element and the point. So DH is inversely proportional to the 1 by R square. Now if we just accumulate the three equations, combining these three, we will get DH is equal to IDL sin theta by R square. So if we want to remove the proportionality constant, we will get IDL sin theta by 4 pi R square. Where is the 1 by 4 pi R square is nothing but the constant, proportionality constant. Again, we know what is DH. DH is nothing but so we can write H is equal to IDL sin theta by 4 pi R square. But the integration is in the closed path. Why closed path? Because current can only flow in the closed path only. Now we know B equals to mu into H. So what is B? B is equal to mu IDL sin theta by 4 pi R square. So this is known as the Bio Savart's law. So this is the Bio Savart's law. Now we already got the B is equal to H is equal to IDL sin theta. Now if we want to write it in the vector form, what will happen? We know that A cross B is equal to AB sin theta. And if we are taking the unit vector A and unit vector B, so it will be A B sin theta. Now as these are the unit vector, the magnitudes are 1. So we can write sin theta. Here also we have one sin theta. So we can write it like DL cross AR. What is AR? AR is the direction of the radius. So we can write DL cross AR. So I is a scalar quantity, we cannot write it. So here we can write that H is equal to I DL cross AR 4 pi R square, where it can be written as the I DL sin theta by 4 pi R square. So this is the vector form. This is the vector form of the Bio Savart's law. Now one important question, using Bio Savart's law, find the expression for the magnetic field intensity due to a long current carrying conductor. Say this is a very long current carrying conductor. We want to calculate the field intensity P. The distance is R. So we already got from the Bio Savart's law, H is equal to I dl cross AR by 4 pi R square. Or we can write what is the dl. dl is the length. So how to get the length? If we have to get the length. So what is the length? Length is, we are thinking this is the dz. So what is this? This is the R dz a phi. We are writing it R dz a phi by 4 pi R square. So what is capital R? How we are getting this equation? So first distance is R. So we have to write the distance in terms of the length and the distance. So what is capital R? Capital R is nothing but the root. For this R, first we have to calculate capital R. Capital R is nothing but the root of L square plus D square. Is this correct? So this is the R square. If we think this length is Z and this length is small r, we can write capital R is equal to R square by Z square. Now, what is the capital R? Capital R is equal to Z A Z. If the distance is Z, so it is Z A Z plus, if it is R, R A R. What is this point? It's the Z, comma. If it is in the 2D, we are thinking the X is so, and we are taking like this. This is our x-axis, this is our y-axis, and this is our z-axis. Or we can think this is like a, so we can write this is the z-a-z into r-a-r. So what is our root of r square plus z square? What is ar then? Because we need the ar. What is ar then? R by mod of r. So what is the value? z-a-z plus R A R divided by root of R square plus Z square. Now we are calculating the dl cross AR, because according to the formula we need dl cross AR. What is dl? dl is nothing but the ZAZ. So we are writing this is a current carrying conductor, so we are thinking it as a cylindrical coordinate. So AR, A phi, AZ. In the first case, DL 0, 0, DZ. What is the AR? R 0 minus Z. So if we are calculating this, we are getting RZ A phi. So what is H? I R DZ A phi by 4 pi R square. Now assume that Z is equal to R tan theta. If this is the Z, and we are assuming that Z is equal to R tan theta. So what is dz? dz is nothing but the R sec square theta. So what is Z square? Z square is equal to R square tan square theta. Now what is the range of the line? Z can be minus infinity to plus infinity. So if Z is equal to minus infinity, theta is equal to pi by 2. If Z is equal to plus infinity, it is pi by 2. Now we are just putting the value in the equation. So we are keeping the value here, integration IR dz divided by 4 pi r square. We are substituting the value, and after substituting the value, we got the value of H as I by 4 pi r into sin alpha minus sin beta a phi. So this is the Bio Savart's law for a very long line. Now one small problem is there. A current of 1 ampere is flowing in a circular coil of 10 cm of 20 tons. Calculate the intensity of the magnetic field at a distance of 10 cm on the axis of the coil and at the center. So first we will calculate the magnetic field at the center. So circular coil for 1 ton, the formula is H is equal to I into 2R, because H into length is equal to I. So for 1 ton for a circle, it is H by I 2R. So if for n ton, it will come Ni by 2R. So what is the value of the n? It is 20 tons. What is the value of the current? Current is 1 amps by 2R. What is 2? 2 into 0.1. So we will get the value 100 ampere ton per meter. Now calculate the magnetic field at a distance of 10 centimeters. What is the formula? The formula is Ni r square by 2 r square z square to the power 3 by 2. N value we know, I value we know, r square. If r is equal to 10 centimeter, we have to remember one thing. There will be no unit in centimeter. We have to convert it into the meter. So it is Ni into 0.01 divided by 2 into 0.01 plus 0.01, because 10 centimeter, it is also 10 centimeter to the power 3 by 2, and we got the value 353.5, and it will be the unit will be the ampere ton per meter. The unit will be always ampere ton per meter. Next, there are 2 points C 523 and P 412. Calculate the ideal value is given 4ax plus 3ay plus az ampere meter. Ampere is the unit of current and dl is the unit of meter. We have to calculate the C at dh at point P. Find dh. So what is the formula? We know I dl cross AR. What is the H calculation? We need this term. What is AR? AR is nothing but the R by mod of R. So what is R? R is, we have to take the point. What is the point? P is the end point and C is the starting point. So 4ax minus 5, I am just writing directly, minus ax minus ay minus az by root of 3, 1 square plus 1 square plus 1 square. So what is the ideal into AR? Ideal value we know. So how to calculate? AX, AY, AZ. So what is ideal? I am taking the 10 to the power 4 constant. 4, 3, 1, minus 1, minus 1, minus 1. Sorry, minus 1 by root 3, minus 1 by root 3, minus 1 by root 3. If I multiply, if we do the multiply, we will get the value H is equal to IDL. So you can see H is equal to IDL 10 to the power minus 4. We are just putting the value, and from there we can get the dH value. Extract the expression for Maxwell's second education. So Maxwell's first equation tells about the Gauss law. We will discuss about the Maxwell's second equation. So from the Gauss law we can write that the magnetic flux, from the magnetic flux we can write that magnetic flux in a given surface is the surface integral of the flux density. So for the electrical Gauss law we know that the psi dot ds is equal to q, or what is q? Q is known as the electric, sorry, we can write q dot ds is equal to psi, is equal to psi. So what is psi? Psi is q is equal to charge enclosed. What is psi? Psi is the total lines of flux. So integration of q dot ds is equal to psi. Psi equals to, now if we go for the magnetic flux density, psi is equal to b dot ds. B is equal to the electric flux density. Now, so for here it is the d dot ds. What is b? B is nothing but the magnetic flux density, and we write it generally by, but in practically there is no it is I told in the first topic only, it is a fictitious quantity. So practically the flux density is 0. So we can write that b dot ds is equal to 0. Now if we change it into the, using the Stokes theorem, we can write grad b dot dv is equal to 0. So grad b is equal to 0 is the Maxwell's second equation. So next we will discuss about the Gauss law in vector form. So as we discussed already, we will come to the Gauss law in the vector form. So for the vector form, we already know that we discussed that flux density D is equal to D dot psi s. If there are the lines of flux and this is a surface, so D is equal to psi by s. So if we are thinking about a very small equation, so d psi is equal to total number of lines crossing normal to the surface of the area ds. What is d psi? D psi is equal to total lines of flux crossing the normal to the surface ds. And what is ds? ds is equal to the surface area. So, and an we are telling about the direction of the differential equation. So if we are writing the Gauss law, we know Gauss law, according to the Gauss law, we can tell that the number of the flux density in a closed path is equal to the charge enclosed. So here we can write D is equal to, D has some direction. So we will write D dot ds, and ds direction we are taking as an is equal to q. So this is the Gauss law in the vector form. What are the application of the Gauss law? Using the Gauss law, we can calculate the infinite line of charge. Say we have a infinite line, as we discussed in the magnetic field, same thing. We have an infinite line and we have the cylindrical in nature, and consider the line charge from rho L coulomb per meter and along the z-axis. So consider this radius, consider the radius is r and the total length is L. So we can calculate the infinite length. Consider the differential surface area. This is the differential surface area ds, and the radial distance from the center is the r. So the direction of the surface is along the AR direction. So this is a z axis and there cannot be any component of the d, because as this is a line charge, the lines of flux will come out from like here. So there will be no component along the z direction. So d has the radial component only. And as the from the Gauss law we can write q is equal to integration of d dot ds. We can know q is equal to d dot ds. So we will take the integration q d dot ds of the top, bottom and side. As there are no top and bottom component, only we will consider about the side component. So d dot ds is equal to d r d phi dz, r d phi dz. So what is the r? 0 to pi and dz is 0 to l. If we integrate it, we will get it is 2 pi r dr l. And we also know that the dr is equal to q by 2 pi r l and d is equal to epsilon e. So what is e? E is nothing but the q by 2 pi 2 epsilon pi r l a r, and this is also known, and what is then this is also known as the Coulomb's law. This is also known as the Coulomb's law for the surface area. This is also known as the Coulomb's law for a cylinder. So the question may come, the calculate the Coulomb's law for the cylindrical area, and what is this? E is equal to rho L 2 pi epsilon r into AR. And we can also calculate it for a coaxial cable. What is the meaning of the coaxial cable? Coaxial cable means two cables are together and they have some common axis. So one axis is A, another axis is B, and the total length of the cable is L. So we can calculate the charge distribution from the inner surface as well as the outer surface. Say the charge density is the rho s coulomb per meter. The total outer surface area of the inner conductor is 2 pi AL. So what is the rho s? We can convert the rho s in terms of rho L because it is easy. So rho L is equal to rho s into 2 pi A, because rho L is equal to Q by L. Rho s is equal to Q by L into A. So if we compare these two things, or we can write s is equal to 2 pi RL, as this is a cylinder in nature. So if we compare these two, we can write rho L is equal to rho S by 2 pi A. Therefore, the line charge density has been changed into the rho L. If we know, this is I have already discussed. So if we put the value now for coaxial cable, we have A and B. So we got D is equal to rho L 2 pi R. In place of rho L, we are putting rho S into 2 pi A. So we will get that D is equal to rho S A by R for the coaxial cable. So all the every flux is starting from the positive charge of the inner surface, you can see from the red, and it is go to the terminate on the negative charge of the inner surface of the outer. So if this is the positive charge, the inner surface of the the outer surface of the inner cylinder, it will go to the inner surface of the outer cylinder. So this is the another application of the Gauss law. Another application, so we can also write Q inner is equal to rho inner 2 pi AL, Q outer is equal to rho S 2 pi BL. So this is only for the cylindrical coaxial cylinder. Similarly, we can calculate it for the infinite sheet of the charge. So if there is an infinite sheet, we can also take the rho S and we can integrate it, and we will get Q is equal to 2 integration of d dx by dy. Here also we will not consider when this is a surface. There will be only the radial component, no outside component. So we are taking d dxy top and bottom because there is no xy side component. There is no side component. So same thing, we are integration it and we are getting Q as top and bottom means same surface. So we are calculating 2y is d dot dx and dy, and again what is dx and dy? Dy and dx is equal to A is the cross sectional area, and if we put the value we will get d is equal to rho s by 2. So today we have discussed some important question. So for today's lecture we have discussed about some important questions on the Coulomb's law. We have discussed about the Gauss law, what is magnetic field intensity, and we have solved some problems. So thank you all.
Like, share and subscribe. Hit the bell icon for more updates.